Alright, the purpose of this fifth video is to talk about the angular version of momentum, but we're going to have to split this into two parts. So this is part one.
There are two different positions the diver can use.
Let's take a look at angular momentum in action.
There are two different positions the diver can use. Rotational inertia is controlled by the diver's length of his body. Therefore, if the diver uses a straight or a tuck in the dive, he will either speed up or slow down.
If the diver uses a straight or a tuck in the dive, he will either speed up or slow down.
In the tuck position, the diver's rotational velocity will be faster. In the straight position,
the diver's
rotational velocity
will be faster. In the straight position, the diver's rotational velocity will be slower.
So let's try to answer some questions about this diver. Go ahead and pause the video, read the questions, and see if you can answer these and give a justification for your answer. Alright, let's resume. So the first one is the diver's translational momentum conserved. Well, we know that translational momentum is only conserved if the net force is zero, and so no, it's not conserved because there is an external net force on his center of mass. Remember, translation means center of mass. We're only analyzing what happens to the center of mass. And the center of mass of this diver is being acted upon by the non-zero external net force of gravity. So, in other words, he is accelerating translationally. How about the second part? Does his rotational inertia change even though his mass is constant? Well, rotational inertia is the proxy that we use for inertia when we analyze extended bodies that rotate. So there's more to it than just mass. Remember, it is given by a formula, and that formula, depending on the object you're studying anyway, is that I is proportional to mr squared. So for instance, we did problems where we did like a solid sphere, so I was then equal to the constant 2/5 times mr squared. Or for a particle, I is equal to 1 mr squared, or just mr squared. The diver is an irregular shape, so we could choose to model him as, like a rod or something, but that's not really important here. All that matters is that we know we can change I even though mass is a constant because we can change r. So when the diver tucks into a ball, he is decreasing his r value. And let's just try to remember what this r value refers to. This is how far from the rotational axis each particle in his body is located. So when you rotate something, it is harder to rotate an object if it is farther away from the rotational axis. Therefore, tucking brings more of the diver's mass closer to the center of rotation and therefore decreases the r value, which decreases the I, or inertia value. One last thought here in this first part of video 5. The angular momentum vector. We need to know which way it points, just in case that should come up. It comes from the formula. So L is equal to I omega, or we could say that the angular momentum L is proportional to the angular velocity omega, and therefore, since these vectors are directly proportional, they must point in the same direction. So do we remember which direction the angular velocity vector points? that would be given by the right-hand rule. Quick reminder of the right-hand rule. Stole this off Wikipedia. It's got a lot more information than we actually need to look at, but regardless, it's always good to have more information. It's better than not enough. So what we're going to look at here is the vector in this sort of light green, aquamarine, seafoam color, whatever you call that. And depending on which way this thing is rotating, it's going to change direction. So now it's up, and then it's going to rotate the other direction, and the angular momentum is down, and back to up, and so on and so forth. Now, it doesn't show it on this GIF, but we could also draw a vector that shows the angular velocity omega. And what direction would it point? Always in the same direction as this green, weird-looking green vector. So now it would be down, and then when it rotates the other way, it would be up, and so on.
If I spin the bicycle,
so here we have a really cool consequence of the conservation of angular momentum, and I'm going to let this guy explain.
But if I spin the bicycle wheel clockwise, clockwise. But what happens if I spin the wheel? I change the spin direction by twisting the wheel upside down. But what happens if? Well, I change I spin the wheel clockwise direction by twisting the wheel upside down.
Before he shows, let's think about what he's doing. When he twists the wheel, doesn't just hold it as it's shown right now, and let it spin, but he's going to turn the wheel. He will be turning the angular velocity vector, which is pointing either straight up or straight down, depending on which way he spins this wheel. By turning it, he will be changing the velocity, so literally accelerating this wheel.
See what happens. I'll spin the wheel clockwise, and then I turn it around. Anti-clockwise.
So let's try to make sense of what we just saw. We know that as long as there is no external net torque, the angular momentum of any system is a constant value. It doesn't change. Therefore, assuming that the guy with the bike wheel was in an isolated system, which is a reasonable assumption, we'll say he was on a frictionless rotating platform, or a platform capable of rotating without friction. If you change either I or omega, the other quantity must also change, so that this L doesn't turn into a new number. It has to stay a constant. We could also equivalently state that the rotational inertia is inversely proportional to the angular velocity for an isolated system. What would happen then if you change the rotational inertia of the system? That is going to lead us to our next video.